Okay, we're gonna get started here in a second. Oh, here it is. Okay. All right, we're back. Um, so that's just a little. So we reviewed the homework a little bit, and we just talked about a little bit more, slightly more complex factorial design for ANOVA. And there's a reason for that, which you'll see for your homework, and actually you'll see more clearly next week. All right. Um, And it does help to understand how ANOVA is breaking up these variances because we may see something like it later this semester. All right, great. And last of all, I wanted to put in your ears this idea of interactions because we will see that in a much more powerful way later this semester as well. All right, okay. Um, 1 second. Okay, so I want to go back to, so let's just forget everything we've done this semester for a second. And I want to go back to something that we talked about like really in the beginning of the semester, all right? And do you remember this image? Do you kind of remember some picture like this in the second week? All right, great. It's not just me. You were all here then. All right. um, so in the beginning of the semester, I kind of showed this picture and I talked about statistical inference. And I just want to get back to it for a second to remember what we're doing, because now we've gotten into the thick of writing code and doing computations and we're getting results. Life seems good. We're getting p-values and we're like on our way. But I want to just stop and go back and ask, are we really doing what we said we're doing? All right. Um, so what I mentioned in the beginning of the semester is that this thing we call statistics, it seems like this great magic trick where we get some data, we run some statistics on it, we get some other numbers like F statistics and T statistics and p-values, and we can now say something about people who we haven't even measured, right? Like, for example, the example I just did of the cram school, they're just doing it on, let's say, 18 students. They're just doing this experiment on 18 students, but then they're making a conclusion that is broad to all the possible students that they could have, not just about those 18 students, right? They're not saying, oh, this is an experiment of 18 students. They're saying that we've done an experiment on 18 students, but now the conclusions we have, we believe these would hold for any students, any group of students, all right? So they're doing something we call inference, where they're looking at a sample and they're drawing a conclusion about a larger population, all right? And that's the reason we're doing statistics. We're not doing statistics to just describe the data that we have, because that's really easy. We don't really need anything too powerful to do that, okay? Um, and I just wanted to remind you that this magic trick is not simply what we often imagine, which is we often imagine we start with these measured variables, we measure some variables, we do some statistics, and bang, we suddenly can say something about a population. That is not exactly how it works, though it feels that way because we start with data, which is this, we then perform this statistics, and then we suddenly say something about the population. It seems mechanically that's what we're doing, but we should be doing a lot more than that to be able to draw these conclusions. All right. So just a reminder, we should be um, able to say that the data that we're collecting is really describing the sample that we are observing. So meaning, if I have, so in that previous experiment where like we took 18 students and they, some of them did a short program, some of them did a medium-term program, some of them did a 10-week program. First thing we want to be able to say is that the data that we measure, the variables that we measured accurately represent those 18 people. That is not always the case, and I'll get to that in a moment. All right. So is the data we got, does it really represent the people we're interested in, if it's people that we're studying? All right. If it is, then we can perform these statistics that we've been discussing this semester. All right. Once we've performed the statistics, what we're really getting is some numbers that represent the sample. And then we're doing another little magic trick where we're saying, now these results apply to a big population. But in fact, these only apply to a bigger population if the sample that you were working with is reflective of a bigger population, like if they are representative of a big population, right? And most of us, we worry, are we doing the statistics correctly? Like, am I using the right function? Am I using the right formula? But for most of us, most of you, most of me, most of people like me, that is not where we make our mistakes. Where we make our mistakes is in these other two inferential leaps, these assumptions we make that the data we have accurately represents our sample and that the sample we have is a good representation of the population I'm interested in. That is typically where we make our mistakes. And unfortunately, it often feels like there's no math to describe those mistakes. So we just pretend we're not making those mistakes at all. We just get obsessed about, are we using the right formula, which is important, but it's not everything. So really what we're calling statistics is like three jumps. One is an inferential jump where we assume that the data represents our accurately measures our sample. Then we perform statistics. That's the mechanical jump, like a statistical jump or a computational jump. And maybe we do bootstrapping or something. But then we have one more jump to make, which is to assume that the sample actually represents the population we're interested in. All right. If we make mistakes here with our measurement or here with our inference, the statistics we're getting are not actually accurate. They actually do not give us accurate answers, right? So in those early weeks of this class, when we were all young and foolish, all right, I also showed you this picture, and I'd like to come back to it a little bit now. Okay, so in this picture, these two pictures, there's a little path on the left and a path on the right going from top to bottom. These represent these two paths. This left-hand side path called measurement reflects all the things you have to do to make sure that the data you're getting really describes the sample you're interested in. And the path on the right called representation is really reflecting all the things you have to do to make sure that the sample of people you're looking at really represents the population you're interested in. All right. And what I described earlier, and I'm going to go over it just briefly here now, is that these are not simple things. There's multiple things you have to kind of make sure typically. We're not doing this much in this class because this is a computational stats class, okay? But I will try to do some things where we can kind of visualize how mistakes we make affect our results. I'll give you a little intro to that in this class. And then for the homework, you're going to kind of do a couple of simple simulations to see how making mistakes affects your results. All right. But just to remind you what these two paths are, because it's been a long time. All right. Typically, we are not measuring exactly what we want. What we want, the concept that we're interested in, is often quite a bit different than the measurement items that we use or the things that we use to actually measure it. All right. So the example I might use is in this example right here. For example, remember I said that the ability of students, the scholastic ability, the school ability of students, I'm classifying students as average, outstanding, or below average. And I just briefly mentioned that one way we can do that is to look at their grades. All right. And if their grades are average, we say this is an average student. If the grades are above average, we say this is an above average student. If they're below average, we say this is a below average student, or at least as a student with abilities below average. Okay. But I want to be really clear about something here. What I'm interested in is their academic ability. I'm not actually interested in their score. We are hardly ever interested in the thing that the data says. We're interested in a bigger concept. All right? So I'm interested in their academic ability. So I got a question for you. Be honest. Are your grades, oh no, this is the scores. Are your grades that you get in class an accurate representation of your academic ability and how much you've learned? Oh, you all say no. That was quick. You were waiting with that answer like in your gun, like psh, no. Well, okay, why not? If you say no, you got to say why not. Who said no? Billy, you said no, right? Now do you regret it? No, okay. Why not? Give me a reason. What? TA, subtract 5 points from everybody, okay? Just got to bring them back to reality. So sometimes you can have a good grade, but you didn't learn that much because. Okay, okay. Oh, got it. So like when I give you the code and you just copy the code and you just change a little bit, is different than if I didn't give you the code and you just do it entirely by yourself, right? And you're saying you prefer it that way, right? But you're right. But you're correct, right? Having to do it entirely by yourself rarely demonstrates whether you learned it or not. Definitely is true. Can somebody give me another reason why your grade may not reflect your ability? Ah, right. What? Yes. What you're describing is what we teachers call being a professional student. It means you've mastered how to get good grades without having to learn anything, right? We call that a professional student. Oh, you forget it's the same thing, right? Yeah, sure. I mean, there may be tips and tricks that you know to be able to get a good grade. Maybe you learned some trick like, hey, the professor always asks a question like this. I'm sure it will be on the exam, right? But you don't really have to learn it. You just have to memorize how to solve that problem. All right. So, okay, so you've given me two reasons why you may not be that academically able, but your grades are high. What about the other way around? Is there a reason why maybe your grades are low, but you are academically very able? Oh yeah, these are the excuses I want to hear. Okay. Yeah, sure. Maybe you're a nervous test taker, right? The time pressure, but not for homeworks, right? Well, this is one of the reasons I don't give tests in this class because, like, I don't know of any, like, there aren't many situations I feel on a job where they're like, you've got 1 hour to solve this problem. Go. Oh, and you cannot use your internet. What? Why not? Right? So, I mean, that's one of the reasons I don't do tests because I don't feel it's a fair representation of how we. I mean, if you talk to a real data scientist, like I told you in the beginning of the semester, they have RStudio open on this window and they've got Google open on this window, right? Because you or Stack Overflow open on this window. So you just like you are copying by default. So and again, one of the reasons I encourage you to work together, though I don't want you copying each other, but I do want you to work together because that's you will collaborate forever in your careers. Okay, but this is a good example of how the data we have is never the concept that you're interested in. All right, you have to really be a little bit dishonest to yourself if you think that the concept and the data are the same thing. They're rarely the same thing. They're hardly ever the same thing. Okay. Um, and I will even say this, sometimes I talk to people and they say, yeah, but that's not true for, maybe some analysis. Like maybe I'm really interested in the profit of the company, so I'm literally looking at their profit numbers. All right. That's true. Maybe you are interested in like the profit numbers, but maybe when you are describing profit of a company, for example, maybe you're interested in their profitability, meaning their ability to make profit rather than the actual profit. It might be a little bit different. So I always feel that there is a gap, usually quite big, between the concept you have in mind and the data that you have, right? Um, so if your grades are not an accurate representation of your ability, why do we give you grades? Why do you accept? You're the paying customer. Why don't you like have a rebellion and say, no, we're the customer. We don't want grades anymore. Why do you accept grades? I'm curious. This has got nothing to do with the class. I'm really curious. Yes.
Yes, it serves as a measure to know how maybe responsible one person is compared to another. So it
Oh,
could,
so actually, this is interesting. So there's two things. One is at least it's a measure. It's a number. It's easy to analyze. Okay. If I had to go and understand every single student's, it would take forever. It's much easier to like give an assignment or an exam and just get a grade. Okay. So that's definitely true. It's easier, even though it can be a little bit fuzzy, right? But then you might mention something else. It's also measuring like how responsible you are potentially, right? So even though an exam may not measure your ability, it does measure maybe how serious you are about the class. Maybe you just studied and studied and crammed and just like memorized everything just because you are serious about the class. So I didn't measure your ability, but I did measure your seriousness, right? It's possible, but there realize that concept is now drifted from what I am originally wanted to measure, right? So there's this drift in the concept. So this is true, and in this picture, I just wanted to show you that there is a difference between what I'm measuring and the concept I'm interested in. All right. Um, and what I'm measuring might be something like your grades. But the grades, let's say exam grades for a moment, but the exam grades, but the concept I'm interested in is your academic ability in the class. But the exam grades may not be an accurate representation of that concept. Instead, it might measure some other kind of construct or concept. For example, it might measure your seriousness. But I think, you know what? I may think that seriousness is close enough to ability. Good enough. All right. So there's three things there then. What I'm measuring, what the measurements are actually measuring, like the actual concept the measurements reflect, which is what we call a construct usually. But then the concept we're interested in is usually something that we cannot measure easily. All right. Again, not always, but often. Not always, but most often. All right. So there's a difference between these things. So if there's a difference between what I'm measuring and the concept, there's two types of validity problems. One is called construct validity, the other I'll call conceptual validity. All right, so let's say someone says, hey, grades does not measure ability. And I say, yeah, but at least it measures seriousness. Seriousness is my construct. All right, but do grades really accurately measure seriousness? Again, we can have an open question about that. And again, we can find potentially problems in those assumptions. Okay, like maybe somebody's really serious about the class, but they're having some family crisis or they themselves are sick and so they couldn't get the grade they wanted. Then I have a problem. I'm not measuring even seriousness, right? So I could make mistakes even assuming grades measure seriousness. In any case, I'm not interested in seriousness, I'm interested in ability. And the degree to which seriousness and ability are the same thing is again something I can challenge, right? I can say, yeah, I mean, there are many students who are serious about getting good grades. They're not serious about having good abilities. So there's an issue there as well. Okay. Um, but let's go down the line. There's even more problems I can make. Okay. So let's say I'm measuring grades. How am I measuring those grades? So forget seriousness and ability. Like we've already decided those are difficult, but just grades. Am I even actually accurately measuring grades? So maybe like, for example, that cram school, that example that we saw, maybe to understand whether you're outstanding, average, or below average, they ask you, could you tell us your GPA, your average grade for the years you've been in school so far? Okay. Um, we have to also ask if the data we're collecting is really the thing that we think we're measuring, right? I mean, we're interested in grades, and but the data we're actually collecting is GPA, and we need to be maybe sure that grades and GPA are the same thing. They might be, okay? Like my GPA is supposed to be my average grade, so that might be a fairly accurate representation of grades, even though grades is not the concept I'm interested in. But there are many situations where that is not true necessarily. All right. Why? Well, let's say, for example, that I'm interested in students' grades, but what I'm actually collecting is their letter grade, like A, B, C. Like you could get an A grade, a B grade, or a C grade. And this can be a little bit problematic because two people could have, one person, let's say, for example, not in my class, but one person could have like 89%, and one person could have 90%. And imagine for some professors, not me, but imagine for some professors, the 89% is a B plus and the 90% is an A minus. And they've got different grades, even though they're only off by 1%, right? Um, so there can be a little bit of a gap even between what I think I'm measuring and what I'm actually measuring. All right. So I could say, yeah, this is a B student, this is an A student, but they were only off by 1%. So actually, they should be pretty much getting the same grade, but they're not. All right. And in a GPA or something like that, that often matters. All right. Like in the US system of measuring GPAs, like what is it? An A plus is, I forgot, A plus is 4.0 or something like that. A or A minus is 3.5, something like this, right? But you might be off by just 1%, but your GPA is now quite a bit different from other people. All right. So there could be errors in how we're actually measuring the thing called grades. All right. So forget the concept problem, forget the construct problem. We even have like a measurement problem as well. All right. And last of all, how we are processing this data could also cause some errors. Let's say I'm collecting people's grades and it's like, 89.45, 81.23, and I just round it off. I say, 81, 89, good enough. All right. Rounding it off could also introduce a little bit of error into my data as well. I don't know how exactly, but it might. It depends how I round it. Do I just delete the fractional value? If you get 81.6, do I make it 81 or is it 82? All right. So I could introduce a little bit of error based on how I'm processing the data that I'm getting as well. All right. So one of the things I want you to be aware of is that in this picture, even though we are so happy to get like some data and run some statistics on it, before we even run the statistics, we could have made a whole bunch of mistakes that are affecting our results. All right. Um, On the other hand, there's also a whole other types of mistakes I can make on the right hand side. So I've performed some statistics, I've got some numbers, and now I'm about to describe a population that I did not measure, but I'm going to try to describe them with the results of a sample I did measure. Okay. Here too, we can make a whole bunch of mistakes, and I'm kind of drawing them as these separate things that can go wrong. All right. So one is the people that I'm interested in describing, we call them like the target population. All right. So the cram school example that I used, they may be interested in saying, does our preparation programs, are they effective for students who join our cram school? So their target population is students who are customers of their cram school, not the students this year, but any student in the past, present, or future who might be customers of their cram school. That's their population they would like to describe, right? Um, However, they don't have access to students past, present, and future. They have just access to some students right now, right? So the students who they're targeting, who they're actually targeting, is what we call the sampling frame, right? So the sampling frame, they might say, let's just try this program. We're getting 18 students who are interested in the GMAT. Let's use them as we're interested in students who enroll in our GMAT preparation programs this year. That's our sampling frame. That's the students we're really interested in. Excuse me, that's the students who we're going to try to get data on. All right. However, it is a big issue. Are the students we're getting this year, are they representative of students we got last year, in the future years? Does the sampling frame really represent the population in general? It may not. I don't know, right? Like maybe this year there's not so much demand for GMAT because GMAT is usually often asked by, let's say, US schools for business education. Maybe not by Taiwanese schools, I don't know. So, and because of COVID, maybe many students are not planning to go to US schools this year. In fact, that's a fact. Because of COVID, a lot of students are not going to abroad or not going to other schools outside of Taiwan this year. So, as a result, the students I'm getting this year are not even the same as the students I would get in previous years or in future years, potentially. I hope. All right. Assuming we control COVID. So there can be a problem between the students that I'm targeting and the students I wish to describe. And I'm not even talking about the actual students who I'm getting. I'm just talking about the students who I'm targeting, like students who will enroll in my GMAT preparation program this year. All right. The next problem is, who are the actual students who come to this year's program? Are they even the sampling frame that I had in mind? They may be, they may not be. All right. Um, it's possible that the sample I actually get is not the same as the sampling frame. Why might that be? Um, for example, bless you, I might be targeting students who are going to enroll in the class this year in my preparation program this year, but for some reason outside my control, the students who actually show up may not be those students for some reason. All right. For example, it might be possible that this year, because my GMAT program preparation program is new, I'm offering it at a discount. I'm not charging as much as I usually would. And as a result, there's a whole bunch of students coming in to take my class who would never ordinarily come to my cram school because they can't afford it or they're not interested in it that much. Okay. But because I've offered an incentive, I'm getting a different set of students than the ones I should be targeting, even. Right. Then the students who I actually measure may not even be my sample. Like originally, it's possible that, 100 students come to take my GMAT, but let's say a bunch of them drop out in the middle. Then the data I get is not even the sample I began with, right? Like some people have dropped out. And then finally, for other reasons, I might disqualify some students in as part of my experiment for some other reasons. I don't know what that is. Okay, maybe I find out, oh, some students were also self-studying GMAT on the side with a popular book. Well, I don't want to include them in my study because they were doing some extra preparation. So I remove them. So that also causes some adjustment that affects my data, right? So my point is there's two whole families of problems I can have. One on the measurement side about what am I measuring, and then one on the representation side, who am I measuring? All right. And I can make so many different types of mistakes on both sides of this thing. And if I'm not careful to try to minimize or eliminate as best possible these mistakes, then these statistics that we've kind of done these past few weeks are kind of meaningless because they're describing something we didn't really intend to describe. All right. Okay. Now the question is, if I do make one of these mistakes, how many are there? There's a whole bunch of mistakes here that I could make. 1, 2, 3, 4, 5, 6, 7, 8. I've listed at least 8 different types of mistakes you could make. Some of them I'm calling conceptual validity, construct validity, measurement error, processing error. Some of them I'm calling coverage error, sampling error, non-response error, adjustment error. Okay? So many mistakes I could make. How do these mistakes affect my data is another question that you should be kind of aware of. Why? Because you cannot eliminate all the mistakes in the world, but you might have some sense of how these mistakes affect you. All right? And there's two ways in which mistakes can affect you. So I'm going to just show this. It's not a formula, it's more like an expression saying that if there's a variable that I'm really interested in, let's imagine that's the population mean of some kind, okay? There's a variable that I'm interested in. Excuse me. There's a variable that I'm interested in. However, when I'm trying to measure this, there's some error associated with measuring it. So the final measurement I make is something else that I'll call y, okay? What I really wanted to measure was mu, meow, meow, and and however, there's some error creeping into this system. All right. What kind of error? I just told you these 8 different types of error. Okay, stop asking me. All right. How does it affect us? And there's 2 ways it can affect us, and we need to be aware of both types. All right. One way that it can affect us is bias, and the other way it can affect us is it adds to our variance. So let me try to describe these a little bit. It's possible that I'm trying to measure something, but I'm making a mistake in measuring it. Or it could be a measurement mistake, it could be a representation mistake, okay? But let's start with the measurement mistake. It could be a measurement mistake. And if I'm making the exact same mistake on everybody, then instead of measuring mu, which is this dashed distribution, I'm measuring y, which is this solid distribution, okay? For example, let's say part of my research, let's say I'm trying to again do something about grades and student performance, blah blah blah. But one thing I want to measure is your age, right? How do I measure your age? I ask you, how old are you? And um, hopefully you all give me a fairly honest answer. However, when you tell me your age, are you really telling me your accurate age? I don't think so. Because let's say, for example, that you're 22 years old, lucky to be you, um, but it's actually your birthday tomorrow, and you're still telling me I'm 22 years old, but actually you're 23 years old because your birthday is tomorrow, right? On the other hand, somebody's birthday is today and they just turned 22. So they're like, I'm 22 years old. So I'm actually measuring 2 people with the same grades, with the same age. I'm saying 22, but one person is almost a full year older than the other, right? Um, am I going to, okay, so I think if I do it that way, I'm going to make a systematic mistake. Because for all of you, I'm going to get an age that's actually a little bit lower than your actual age, right? Some of you are 22, some of you 22.1, 22.2, 22.9, but to me, you're all 22. I've cut you all short to just 22. Or whatever your age is, I'm just kind of rounding down a little bit, right? So ultimately, when I end up doing my analysis, all my results are off by a little bit because my age measurements are actually all off by a little bit. And here's the important thing, all my age measurements are off in the same direction. I am underestimating all of your ages, assuming you're not lying to me. I'm underestimating all of your ages. Okay? So this produces a kind of bias in our calculations. Moving on. All right. But there's some errors that I can make that are not systematic. They're kind of random. For example, for some strange reason, I'm also asking you, what is your height? I don't know what height has to do with performance, but I don't want to take a chance. I'm going to measure it. Okay. So I ask each person, what is your height? What is your height? Okay. Um, However, very few of us have measured our own height in the last 6 months. You might have if you went to the clinic and they do that little thing on you, right? But unless you've been to the clinic recently, you don't exactly remember your height. In fact, the last height you might remember is the height your parents measured before you left home. You know, like in a lot of homes, you have like their children's heights on the wall, tick, 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 and that was the last height. You know, so that might be burnt into your memory that this is how tall I am. But you've grown a little older, you've been through college, maybe you've not really measured yourself. Okay, so it's entirely possible that when I ask you your height, you're all taking roughly a guess of your height. None of you, I don't think most of you know your exact height like accurately. So some of you may tell me a measurement that's maybe 1 centimeter too little, some of you may tell me 1 centimeter too tall. I don't know. Okay. But if everyone's making mistakes in both directions, some are making too small, some are telling me too big a number, then what's going to happen is that the thing I'm measuring, the variance of your height is going to increase in my data set than the actual variance of your height, right? Um, so this is another kind of error, but this error introduces variance into our system, not bias into our system, assuming the story I've just told you is correct, right? So we can apply this kind of thinking to the types of errors that we've seen here. And maybe I'll play with it with a couple of these. And I'm going to ask you to think about this a little bit more on your homework and give me a scenario or an answer. All right. Um, so, for example, let's say I am trying to do a study about my target population is students who usually take my class. And to do the study, what I do is in class, I suddenly say, oh, we're going to have a little quiz. I want you to all take a really little, don't worry, I'm not going to do that to you. We're going to take a really little quiz and I want to just see like, have you really understood what we're talking about? Okay. Now, I can make two types of mistakes here. One is under some kind of under coverage problem, which is maybe today, or let's say, let's imagine that tomorrow there's going to be like the, what do you call this? The sports day, like there's going to be sports day. So some of the younger students are going to prepare for sports day, so they don't come to class today. All right. Alternatively, I could make another kind of mistake, which is maybe today's the let's say I was doing this little quiz in the first 3 weeks of this class. And there were some students sitting here who don't plan to take the class. They're just here to listen and see if they might be interested or not. They are ineligible students to my study, and yet they're in the class, and I'm getting scores from them. All right. Depending on which one of these you have, you might have a bias problem or you might have a variance problem. All right. And as part of your homework, I'm going to try to give you some scenarios and ask you which kind of problem do you have. All right. Because I'd like you to think those through so that even though this is a computation class, I don't want you to come out just being like a computer monkey, like, oh, I type things and answers come out and life is good. I want you to think about like what are the other problems that could happen before I've even typed the first line of code. All right. Okay. Cool. Um, all right. Let's keep talking about error. So we're making mistakes. So what if you make a mistake, right? Like, okay, I've made a mistake, fine, but I can still do my statistics, like the math still works, and I get my results. What kind of mistake have I made? How does it affect my conclusions? All right. So I want to talk a little bit about now what are the types of errors or types of mistakes we're going to make. You know where I'm going to. It's going to be type 1 and type 2, but let's talk about it for a second. So I'm going to skip through the slide. It's just, but typically, when we're doing a hypothesis test, to me, it's like a legal case. It's like a court case, right? When you go to courts, well, in every legal system in the world, what is the first assumption you make in every legal system in the world about a case? Right. You assume the defendant is innocent, and you have to prove that they are guilty, right? Do court cases prove that you're innocent? Typically not. Typically, the point of a court case is to try to prove you're guilty. If at the end of it, you ask the judge or a jury, is the person guilty? They don't say, no, he's innocent or she's innocent. They just say, not guilty, right? They don't ever say you're innocent. They just say you're not guilty. And hypothesis testing is actually kind of similar to that, right? Um, when we're doing a hypothesis test, we're not actually trying to prove one thing or the other. We're typically trying to find we start with a null hypothesis and we try to find reasons to reject the null hypothesis. All right? And if we can reject the null hypothesis, we say, we do not believe the null hypothesis. Have we proved the alternative hypothesis? No. So just be very careful of that. I know every professor and every stats class says this, but I just want to say it as well, just to reinforce this. We are not proving one thing or the other. We're not proving that the alternative is true. All right? We're not in the business of making proofs. Rather, we're simply saying we tend to believe the alternative. We will support the alternative, all right? But it's not a proof, like a mathematical proof. Mathematical proofs are proofs. We're not in the business of proving anything, all right? And similarly, if we cannot disprove the hypothesis, do we say, oh, the null hypothesis is true, we've proved it? No. We simply say we couldn't disprove it. We may believe it for now, but we just simply couldn't disprove it. Okay, so I just want to make sure that that's the way we are all thinking about hypothesis testing moving forward. All right. So all we're doing is we're either finding support for the alternative, or if we cannot find support for the alternative, we may say that we support the null hypothesis, but we definitely haven't proved it. Okay. Um, and just a reminder again that if this is your null hypothesis in red, as the difference you're measuring increases, your statistic, in this case, I guess a t statistic or f statistic, gets bigger and bigger the further you get from the null hypothesis. Okay, so the further the difference or the ratio, the further away you get. And you remember that if your statistic is bigger than a certain threshold value, like it's in the upper 5% or upper 1% of the null distribution, then we often say, oh, we believe that it's too unlucky to have this number in the null hypothesis world. So rather, we will choose to believe that we're in the alternative hypothesis world, and we will support the alternative hypothesis. Okay. Now, when you do this, again, a recap, there's two types of errors you can make, and I'm sure you've seen this in other classes before. I just want to kind of say it one more time, right? So if the null hypothesis you're trying to disprove, imagine that this null hypothesis is really true, all right? Meaning this red distribution is the real red distribution, okay? If you are unable to reject the null hypothesis, and the null hypothesis is really true, excuse me, that's good. So in this matrix, null hypothesis really true is this left column. Evidence says cannot reject null hypothesis, that's the bottom row. Okay? So if the null hypothesis is really true, and your data says we cannot reject the null hypothesis, congratulations, you're correct. That's a good place to be. All right? You may not have proved a major point, but at least you're scientifically correct, which is good, right? We want to be there. And alternatively, if the null hypothesis is really true, but for some reason you are this unlucky person right here, and you happen to get a data set, a sample where your whatever t statistic or f statistic is significantly different, then you're going to make a mistake if you reject the null hypothesis. Correct? You're just unlucky. And we call this type 1 error. This is a type of mistake you're making, and the mistake you're making is type 1 error. All right? Okay. On the other hand, imagine the null hypothesis is really false. Imagine that whatever the truth is closer to the blue distribution than the red distribution. All right? If the null hypothesis is really false and your evidence, your data, your sample says reject this null hypothesis, congratulations, you are correct. But imagine the null hypothesis is really false, but you cannot reject it with your sample. You're once again the unlucky person, but in this case, you're the unlucky person whose confidence interval includes whatever it is, 0 in a t-test, 1 in an f-test. All right? And you have now rejected the null hypothesis even though it's really false. You have made another type of error, and we call that type 2 error. All right? So generally speaking, these mistakes that I'm talking about up here, these mistakes can translate into one of these types of errors. It can translate into a type 1 error or a type 2 error. You may either reject a hypothesis that is actually true, type 1, or you may fail to reject a hypothesis that is actually false, type 2. All right? What about this thing in the middle that I mentioned, bias and variance? Does it affect you? Can it cause one type of error or the other type of error? Sure, it can, right? Like if the reason I'm unlucky here is because I've measured everyone's age a little too short, a little too low than their actual age in, then I could be unlucky because my age numbers are smaller than they should be, and maybe I'm rejecting hypotheses that should not be rejectable, right? Like this middle point is just too far away from the 0 line, right? Or the other case could be true. Because I've underestimated all your ages, I am unable to reject a hypothesis, and the actually The data I should be getting is a little bit further from the, a little bit further, and I'm not getting that because I've mismeasured the age. All right. So if there's bias in my data, I can cause type 1 or type 2 error. Right? I can either reject something or not reject something, in both cases by accidents. What about variance? What if I don't have bias in my measurements? My average measurement is on average correct, but I've just measured it too wide because in some cases I've underestimated, in some cases I've overestimated. The bias is simply large. Can that cause type 1 and type 2 error? Potentially. So for example, in this case, maybe this would not, maybe this confidence interval should not be so wide. Maybe it should be very narrow. But because I've measured everyone's, let's say, height in this case wrong, some people are guessing a few centimeters too short, a few centimeters too tall. In the end, the results I get also have a higher confidence, have a wider confidence interval. And as a result, I am unable to reject a hypothesis because whatever statistic I'm getting has a wider distribution. Perhaps because the variable I measured has an unnaturally high distribution because I didn't measure it correctly. All right. And the opposite is also possible. I mentioned earlier that we can make a mistake in variance, but the picture I drew was that the variance, actually, the picture I drew is the variance has become too narrow. The variance could be too narrow or too wide compared to the actual population. All right. I can make mistakes in both ways. All right. So in both ways, if my confidence intervals are too wide, I may have type 2 error. If my confidence intervals are too narrow, I might have type 1 error because I'm rejecting things that are not really false. All right. So I just want to reintroduce you to type 1 and type 2 error. Any questions about this? I'll let you play with some scenarios in the homework to kind of just jog your memory of these two types of errors and see how they happen. All right. Couple more things I want to talk about in the remaining 30 minutes. All right. One thing is, let's talk about what these, significance levels and p-values are really all about. Right. So remember, when we are doing our setup of our hypothesis, you're often told we want to be able to reject it at 95% confidence or something like that, right? That 95% confidence is really this quadrant down here. It's saying if the null hypothesis is true, then 95% is this probability, 5%, the opposite 5% is this probability, alpha, right? What we're saying is if the null hypothesis is really true, there should only be a 5% chance that we are making type 1 error. All right? This description is very different than what I told you in the beginning of the semester or than what you might be casually thinking. So when we say, 95%, like we are 95% confident, what does that actually mean? Does that mean that we might only be wrong 5% of the time? It doesn't. It says you might be wrong 5% of the time if the null hypothesis is really true. That if statement is really important. So when we talk about like alpha of 5%, which means confidence interval of 95%, and someone says, I was able to reject this at 95% confidence or with 5% alpha, you might be thinking, oh, they're 95% confident there. They'll be right 95% of the time. But that's not what it means. It means they would be correct 95% of the time if the null hypothesis was really true. Then then the chance of them making a mistake is 5%. That's what this confidence interval of 95% really means. All right. And the reason I'm saying this to you is because you can never know if you're the unlucky person, right? We talked about that earlier this semester. The unlucky person doesn't know they're unlucky. That's why they're called unlucky. All right. If you know you're unlucky, you just change what you're doing. But they're unlucky because they don't know what they're doing. But it's more than that. They don't even know what is the actual probability of being unlucky because the 95% confidence intervals we're using are only 95% if the null hypothesis is really true. All right. If the null hypothesis is not really true, then it's not 95%, it's something else. All right. And I won't go into how to calculate that something else. That's like a more Bayesian approach to doing things. But for that 95% to make sense, you have to have some probability of knowing whether the null hypothesis is true or not. You have to have that prior information somehow. All right. I'm not going to get into how you would know that or how you would use that. Again, that's like a Bayesian statistics approach. All I will say is just make sure that if you're doing this kind of statistics, you don't think that 95% means you have a 95% chance of being right. That is not what it means. All right? It's 95% chance of being right if dot 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 if many conditions. All right? So how useful then are these confidence intervals if they're not what you think it means? Is it useful? Is it useless? Should we just throw it out? Should we use it? Should we just pretend we know what it's about? It's a tough question, all right? If you were to ask, I think, if you were to ask most applied statisticians like myself, people who are applying stats, you'll be surprised how many people make a mistake about what these numbers mean. All right. If you ask them, what does 95% confidence mean? A lot of people will say 95% confidence means I have a 95% chance of being right. And they're wrong. And they're confidently wrong. Right. So it is not what we think it means. Similarly with the p value, right? The p value, if you remember, is the um, percent to the right of your statistic in the null distribution, something like this, right? But you have to be, but the null distribution is only true, but the null distribution only holds if the null hypothesis is actually true. So the p-values you're getting are not telling you, like let's say you got a p-value of 2%. It does not mean you might be wrong. There's a 2% chance you're wrong. That's not what it means. It means there's a 2% chance you're wrong if the null hypothesis is correct, but you may or may not have any idea of knowing if the null hypothesis is correct. All right. So for the most part, I would suggest to you to use things like the p-value or the confidence interval just as a friendly number between 0 and 1 and don't try to ascribe too much meaning to it because it's not as meaningful as you think it is unless you know a lot about this universe and you know your chances of the null hypothesis being false or true or stuff like this, which you rarely do. Okay, so don't treat these percentages as percent confident you're right or wrong. All right, so that's one thing I want to just get across today is just treat them as some kind of normalized number between 0 and 1, and that's, the smaller the better, but it doesn't really tell you how right or how wrong you might be. All right. What the hell are these tennis balls doing down here? Maybe we'll see later. Okay. So that was my criticism of this alpha, or what we sometimes call the significance level. When people say, yeah, my hypothesis is right and it's highly significant, it may not mean much at all. All right, so don't take it too seriously. All right, and in your homework, you're going to see exactly why you shouldn't take it too seriously. You're going to do some friendly simulations to play with that significance level to see what it really means. Okay. Um, on the other side, even if people know what alpha is and the confidence level is, which is 1 minus alpha, we often ignore the other side of this problem, right? Just as there is a probability of type 1 error if the null hypothesis is true, there's a probability of being correct if the null hypothesis is true. There are similar probabilities on the other side. If the null hypothesis is actually false and you are correct in by rejecting it, there is a probability associated with this. The probability of correctly rejecting a false null hypothesis. And that probability, we often call it the power of your test. So when people say, hey, how much statistical power did you have? That's a fancy way of saying, if the null hypothesis is really false, what is the probability that you will come to the right conclusion that it is false? We say that very quickly by saying, what's the power of the test? All right. The alternative, the 1 minus that, is the type 2 error. All right. So most of us know how to visualize the significance level because we think of it as the cutoff point, the area after the cutoff point in the null hypothesis, something like this. We think of that as a significance level. How do we visualize something like the power of a test? Let's take a look. So let's say that this is our null hypothesis distribution right here. It's centered on 0, and this is the null distribution, right? And this is our significance level alpha, this danger zone. This is, by the way, a one-tail test. Two-tailed, you can use your imagination, okay? This is a one-tail test, okay? So this is our null distribution. Now, we could get a t-value, like depending on the sample we have. Let's say we have 3 different samples, sample 1, sample 2, sample 3. Let's say the sample 1, the t-value is here, okay, t1. Do we reject the null hypothesis or no? How many of you say, yes, we reject the null hypothesis? How many of you say, no, we do not reject the null hypothesis? Okay, the rest of you are not taking any chances today. It's like Monday is not the day to make big decisions. Okay. You would not reject the null hypothesis because your t-value is not in this cutoff region. So you would assume that the distribution of t's is not so different from the null distribution. It might even be the null distribution. Okay. What about down here? If your t-value is way past the null, this is way past the cutoff. So your t-value t3 is right here. Do you reject this hypothesis or no? How many of you would reject this hypothesis? Okay, according to the classical statistical way, you would reject this hypothesis, right? And you'd be correct in hopefully you'll be correct in doing so. Okay. Trick question. What if your t-value is exactly at the border? What do? You flip a coin. Not kidding. Let me ask the question another way around. If your t-value is in this situation down here, are you more certain uh, to reject or more certain to not reject? I think you all said you're more certain to not reject, right? So how certain are you to reject? How likely are you to reject? Quite a bit low, not very high. Okay? If you are here, you're more confident in being right, so you're more confident to reject. In this picture in the middle, you're at 50-50. You don't know what to do, right? Interestingly, how, you know, how sure you are to reject this, how sure you feel internally to reject this null hypothesis is kind of visualized in these pictures as the blue area, right? In the 50-50 picture, only half this picture is blue. That's 50-50. In this picture, after you've crossed the threshold, you become more and more sure to reject this thing. And I've drawn this, and this blue area kind of reflects your increasing sureness to reject this thing, right? That blue area really represents if the null hypothesis is false, uh, and can I reject it based on the data? What is my probability of being in this quadrant, assuming the null hypothesis is false? All right. So this blue area, which is actually, which distribution is this blue area under? Is it part of the null distribution? No, it's part of the alternative distribution, right? These bottom three distributions are the alternative distributions based on T1, T2, or T3. In all three cases, the null distribution is the same. This is the null distribution for all three cases, right? This is the null distribution for all three cases. What I'm showing you shaded in blue is the area under the alternative distribution past the cutoff point of the null distribution, all right? And actually that area, this blue shaded area, is what we call the statistical power of your test, all right? It says that is the probability of correctly rejecting the null hypothesis when the null hypothesis is false. Okay? In this middle picture, if the null hypothesis is false and I reject it, I am kind of at a 50-50 point. All right? So I want to show you the power of the test for two reasons. One, it's a very common question when you're doing scientific work to be asked, what is the power of your test? What people are asking you is, if the null hypothesis is really false, how likely is it that, what is the probability that you are correct in rejecting it? Okay, that's what they mean by power of the test. And the way to visualize it is the distribution under the alternative distribution past the cutoff point of the null distribution. So imagine for a moment that T3 was like really high. Like it was like, imagine your T statistic was like 50, 60 or 50 or 60, right? This alternative distribution would be way off the board. It'll be like way off the screen. It'll be way to the right. You have almost 100% power. Alternatively, imagine for a moment that your null distribution, like your t statistic, was like you took the sample and you computed the t statistic, and imagine the t statistic was exactly 0. And your alternative distribution looks exactly like your null hypothesis. What is the power of your test now? If your alternative distribution was exactly right on top of your null distribution, your t-value is 0, what is the power of your test? Is it 0? Would some of this, actually, you know what? Let me make this easier for you. Let's run a little simulation. All right. This one? Is it this one? Ba, 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 ba. No, it's this. Yeah, it's this one. Huh? Okay. Um, ignore ignore all the code. I will give this code to you to play with, but you'll see why you're having trouble answering my question. But when I run a simulation, it'll be much easier. Trust me. All right. So I'm going to run this code. Don't worry what it does. All right. What you want to C is what it shows you. All right. What I'm showing you here is in red the null distribution, and in this case the dashed curve is the alternative distribution. Okay, bless you. As the difference between the hypothesized mean and the actual mean increases, okay, you'll notice my alternative distribution starts walking away, right? I told you, oh, keep walking. Okay, let's just move it along a little bit. If I cannot see it right now because it's just too far off screen, okay? But in this case, what is the power of my test? Is nearly 100%. Almost the entire alternative distribution is past this rejection zone. Is close to 100%. Let's walk this back a little bit. Back a little bit further. Oh, let's go here. Excuse me. Can I, ta-da! Roughly, what is the power of my test now? 50%, right? 50% of my alternative distribution is above the cutoff value of the null distribution, right? It means if the null hypothesis was really false, then I would be, there's a 50-50 chance of being correct at this point because I could reject it, I could not reject it. All right? Let's walk this back to the left. Look at that blue area. What is that blue area in this picture? It's by the way, the blue area, like for example in this picture, the blue area is everything from this point to the right. It's not just this area, it's also this area plus this area. All right? So it's everything to the right of the cutoff on the alternative. What is the power here? Anybody? Alpha or zero? How many of you say alpha? How many of you say zero? One person. Yay! Be brave. But you're unlucky because it's actually alpha. Okay? In this case, my probability of type 2 error is actually 5%. So, no, excuse me, not of type 2 error. My power, not type 2 error, 1 minus. um, my power is actually 5% here. Okay? So, this is one way of visualizing what we call statistical power. So when someone says, how powerful is your test? What they're really asking you is, if the null hypothesis was false, how likely are you to reject it? All right. And what this picture here is saying is if the null hypothesis was actually false, and I'm getting a t-value of 0, but I was to replicate this test 100 times, then we know that 5% of the time I would get t-values in this area, right? And in those cases, I would reject it correctly, right? That's what it's telling us, right? Whereas in this picture, I would reject this. If the null hypothesis was false, I would reject it almost all the time because whatever alternative value of t I get is going to be past the red. So I would be almost always correct by rejecting it almost all the time. If the null hypothesis, if my t value was just on the border, right? Well, depend if I was to conduct this, so let's say my t-value is on average here, and I conducted this test, this test 100 times. 50% of the time, my t-value would be like from here to here. 50% of the time, it would be from here to here. I would be correct half the time because I would be able to reject it half the time. Right? That's the power of your test. Does that make sense? Does that help a little bit? Right? Question, yeah. When is the probability approaching zero? I cannot simulate that easily because I did not simulate this to go below zero, the difference to go below zero. But the difference, yeah, it would have to be to the left. You would, what's that? Oh, this is a one tail. So if you have a two tail, then you start having a probability again going up. All right. I'm only showing you one tail to make it easy. All right. So this is statistical power, just so you know what it is now. All right. Okay. All right, so that's a little description of statistical power. And I'll tell you there's two ways of this. If you actually want to calculate the number, the actual value, there's two ways to do it. Assuming the world is perfect, we don't need to bootstrap, we can just use regular T distributions or F distributions. There's two ways to do it. One is the hard way, but to me it's the easy way, okay? You would first figure out, excuse me, this is the quantile of, excuse me, this is the quantile value. Can I do this? This is the quantile value of the critical value of the null distribution from where you should start rejecting. Okay, so that expression, this QT expression, tells you, it tells you where is this critical value here. It gives you this critical number here. Okay, and then what I'm doing here, this 1 minus pt with this degrees of freedom and this non-centrality parameter, which is just your regular t statistic, this is asking what is the area under the alternative distribution from this point to the right. Okay. So do you see how that kind of works? I'm first calculating the cutoff value, and then I'm asking what is the area under the alternative distribution from this cutoff value. That's the power of your test for a t-test. All right. The potentially easier way of doing this is R comes with a nice little function called power.t.test. You give it your sample size, you give it the delta. Delta means hypothesized mean, sample mean minus hypothesized mean, and the standard deviation of your data. And you should also specify your significant, your alpha, and whether it's one-sided, etc. And this will give you a power value. This will return to you the power of your test. Okay. The power.t.test function is really cool because it can do one more thing. If you know the power of your test for some reason, like you say, I want to do a test and I want to have 80% power, you can run power.t.test, tell it how much power you want, the delta that you are expecting to get, the standard deviation you're expecting to get, the alpha you're using, and this will return to you the sample size you should use. It will tell you if you want 80% power, you need to collect 300, 350, 400 sample size. All right? The relationship between sample size and power will become clearer to you in the homework assignment. Because in the homework assignment, I'm going to give you the code for this simulation, and I will let you play with, if you noticed, I'm only playing with the difference. I will let you play with the standard deviation, the sample size, and the alpha to see how do these things affect type 1 error, type 2 error, power, and so on and so forth. Okay? And I'll give you some scenarios, And you can pick the values you want for those scenarios to see like, how does that scenario affect your power? How does it affect type 1 error, type 2 error? Okay, great. For the F test, this kind of computation is a little bit more difficult because the non-centrality parameter is a little bit more complicated. No problem. Use power.anova.test. All right. So if you're doing, particularly if you're doing an ANOVA, there might be a power.f.test. I can't remember. But if you're doing an ANOVA, you can calculate power using power.anova.test. So here I tell it I've got 4 groups. My sample size is 5. My between treatment variance is this. My within treatment variance is this. Here's my power. Alternatively, this is how much power I want. Here's the setup that I'm interested in. This will tell you what sample size you should have, something like this, okay? All right. I'm going to skip to the last point for today before I let you go. Last 2 points. One is you can do the same thing that we have described with bootstrapping. The reason the whole time we've been bootstrapping, I've been asking you to bootstrap the null and the alternative is because you need that alternative distribution to calculate power. All right. So for example, in your homework assignment last week, remember this was the 95% cutoff. This is the 99% cutoff, okay? Let's take the 95% cutoff. Our F value was actually here. How would we compute the power of the test? The power of the test would be the area under the alternative distribution from this point, from the 95% cutoff. If you're interested in alpha of 5%, it would be from this point where the mouse cursor is all the way to the right under the alternative distribution. And you can do that pretty easily. There's a few steps. First, you've got to compute the 95% cutoff. Just ask the null distribution, where is your 95% cutoff, right? You've simulated the null distribution, just ask it, where is the 95% percentile? You get your 95% cutoff is 2.7 something, right? It's 2.7 something. Now, the area under the alternative distribution is a little harder because we cannot use a nice little function like PT and PF because we don't have beautiful t distributions oftentimes when we're bootstrapping, all right? Or often we're bootstrapping because we don't have good perfect distributions. So what you can do in R, and this is kind of crazy, you can take all the alternative values of f that you simulated, you can pass it to a function called ECDF. This estimates a cumulative distribution function for the alternative distribution. It kind of estimates that density function for you, all right? And you can ask it, and by the way, ECDF returns to you something, I called it alt probs. What it returns to you is actually a function, not a value. It returns a function. You can use this function and give it a value like the 95% cutoff. It will tell you the area to the left of that cutoff. If you want the area to the left or to the right of the cutoff, you just do 1 minus. That's your power. All right. So you can actually compute the power even from your bootstrapped distributions. In this case, by just doing what's to the right of the area under the alternative distribution from the 95% cutoff of the null distribution. All right. Cool. So that's what I wanted to mention, is that all this stuff with power you can not only do with classical statistics. If your data is really weird and you have to bootstrap, you can calculate power through the bootstrap as well. All right. The last thing I'll mention is I know what you're all thinking. You're all thinking, who cares about statistical power? Professor, tell me how you made this amazing simulation. That's what you're really thinking, right? I'll give you the code for this entire simulation. It's really easy in R to make simulations like this, where you can plot something, and then as you change certain parameters, your visualization changes in real time. The way to do it in R is first, um, you draw, you write a function which actually um, plots what you want to visualize. You write a function that does the plot. Simple. And it takes some parameters. Okay? Then you can define those parameters as slider bars, drop downs, text box, whatever you want. And you put all of this within a manipulate function. This comes from the library manipulate that you can install on your computer. Okay? So that way you can manipulate, you can create any kind of visualization. You just create the visualization function, and the parameters that you would like to change, you put them in this manipulate function. You call your plotting function, and all the parameters that you'd like to play with, you make them slider bars or other types of things. You can look at the help menu for manipulate to see what are the different types of user interface elements you can make. You can make slider bars, text boxes to type in numbers, whatever you want. Okay. The other cool thing is once you've made something like this, you can even make it a web application really easily. Just go to this website called shiny.rstudio.com. This is a powerful feature that RStudio offers, wherein if you can write code like this, then with a little bit more effort, you can make this accessible over the web so anyone can come over the internet and play with your simulation. All right? So it's a powerful feature that RStudio kind of offers. So I'll let you think about that, okay? And I'll give you a reading this week to talk about this point here. I won't go into this point right now because we're out of time. We will come back and discuss this last point about statistical power and the future of significance next week in class after you've gotten a chance to read that reading. Okay? All right, great. Thank you all so very much. See you next week. We will start a completely different topic that is not related to hypothesis testing. You'll be happy, I promise you. Okay? All right, see you. Bye bye.